Perfect. Okay, thank you for the introduction. As you already mentioned, my name is Anastasios Vassilopoulos. I'm working with the École Polytechnique Fédérale de Lausanne in Switzerland. Currently, I'm in the, okay, we go directly to this one. I'm at the Composite Construction Laboratory. As you already mentioned, I'm with this lab for 17, 18 years now. And since July, I will create a new group that it's called the Mechanics of Composites group at the same location. So I will skip this next slide with this information, go to the summary of my research activities, just to give you an overview of what I was doing for the last probably 30 years. So this slide summarizes more or less what I'm doing and what I have done, and you can see investigations in different scales from the left part where you see the material testing to the composite components, if you like, testing, and to full-scale investigations that we've been involved in several different applications. So I said that it is an experience that is gathered in the last 30 years, and actually this experience led me to today to start discussing and investing time also on new concepts where I think we can use composites for a novel or innovative structures like this offshore platform that I'm showing in this figure. So the experience that I have is on composites, and it's not dedicated only to one application. It's not dedicated to aerospace. It's not dedicated to bridge engineering. It's a global overview that I gained on composites in different engineering applications, and especially when we talk about composites, you all know better than me probably that we use composite because we claim that they are more sustainable in engineering. And today we have also a lot of proofs for this this claim. We have arguments to support this claim. So we see composites in literally any kind of engineering application that we can see today. So I said that I'm working for 30 years, and for me 30 years is an issue. It causes fatigue. And I was thinking since I was very young, what exactly is fatigue? And after these 30 years, I realized that we have very few idea about fatigue and how it affects a lot of structures in our environment around us. So what we'll try to discuss today, we'll try to discuss about fatigue, introduce fatigue, and explain what fatigue is for those that probably do not have so deep understanding about this. We'll try to touch on the importance of fatigue for composites. And at the end of the day, we'll summarize what we know today about composites fatigue. And I hope that after we might have an idea about what fatigue is. So if we go back to the history, we can see that fatigue is something that is bothering the engineers since probably 200 years, with the first investigation started in Germany. This is 200 years ago by German engineers. It was this engineer called Albert that realized that they had fails in conveyor chains, although they were not loaded at the highest loads that were designed for. And they realized that this was something different than the static loading, than the loading that causes static failures. And they tried to find out what was causing this kind of unexpected failures. Later on, he was the first one that did tests and published something related to fatigue, although he didn't call it fatigue because it was this French engineer, Jean-Victor Poncelet, that wrote the first document in 1841, where fatigue was mentioned as fatigue in something written. So the first time that we see fatigue written in a text, it was in 1841. So later on, we've seen a lot of failures in axles of post coaches, in trains, and that's why we had a lot of investigations. What is surprising is that same types of failures, like train derails due to failing of axles due to fatigue, are still happening today. We have some reports. This is from what I've seen. I'm showing here is from Australia in 2017, and we see that there is a typical fatigue crack on the axle of the train. So due to these failures, there was an investigation, a lot of investigations actually, that were mentioning and documented now that most of the structural failures are due to fatigue or fatigue-related phenomena. Actually, more than 80 to 85% of failures in any structure are today acknowledged as fatigue-related. So this, and also these investigations, or if you like, these observations of failures, led engineers to do more. And the first big program that we had on fatigue of metallic materials at that time was that program that was realized by August Wöhler. Probably you all know the Wöhler curves that we are still using today. So what did he do? He tested, actually I have the paper of Wöhler, the publication of Wöhler. What he did, he tested conveyor chains for different loads. You see here that there was a load. It was a continuous tension compression loading because it was a rotating machine that was applying loading, different types of loads for the to the axles. And then he was reporting actually the time to failure. So imagine that this is my graph. I'm doing a test when the maximum stress that I'm applying is 70 megapascal. I count the number of cycles to failure. It is, in this case, it might be 7,000 cycles. I put this point here, and this is the first point that I have. If I repeat the test at the same stress level, I have the repetition of points that show also the scatter of the fatigue data. I can do it at lower stress level and lower stress level and so on. And this is how we create the cloud of data that produce what we call today the SN curve, what was called before, and it is still called in metallic materials, it is a Wöhler curve. So here I collected from the net an experiment. It's a video, a small video showing the experimental procedure, similar to what Wöhler did. We have a rotating specimen here, this small specimen. We have a load here that causes the stress, and then after some rotations, we can see the failure of the specimen in the middle, which is attributed to fatigue. So we described what happens here when we put the specimen in load, we test it and we record the number of cycles to failure. So this is the procedure that I described before, and then we have the question, what happens in between? So before, because what we see here, what Wöhler did was only putting the data on the SN diagram, as we call it here. So we had another person, it was this Basquin engineer, another engineer that introduced a line, and he claimed that a logarithmic relationship, which means a linear relationship in the logarithm of sigma and logarithms of number of cycles, is capable, is appropriate to fit well the experimental data. And this first, if you like, SN curve has been introduced in 1910. And guess what? It is still used today. This is the most common SN curve equation that we are using today, although others exist, because as we will see later on, there are different ranges of lifetimes that show different failure modes or failure behavior of the material. And today we know that the SN curve is a bit more complicated than this. So then we had the effect of the mean stress. You know that what we described up to this point and what Wöhler did, it was as we said, it was a rotating axle with a load at the end, which means that we had tension and compression of the same amplitude, which means that the mean stress here is 0 in this testing. So if the mean stress is not 0, so for example, if we test only at a positive stresses or only at negative stresses, then there is a mean stress effect. And we've seen today that there is an effect, especially for composites, there is a significant effect of the mean stress. And good for us, there was a good man, his name was Goodman, that developed these diagrams that they are called the Goodman diagrams, that actually what they do, they give equations that can more or less give a relation between the amplitude of the loading and the mean stress of the loading. And in this sense, we can get some relation between these magnitudes, these stress components, and we can quantify somehow the mean stress effect on materials. We'll see later on how this is applied now to composites. What we see is I mean, I had it also before, all these engineers were, I mean, Goodman was a civil engineer, but was working on this investigation of the mean stress effect, and he was also modifying other types of investigations of others. Before we've seen, if I go back, we've seen that, for example, here in this slide, Albert was an engineer working in the mines, but he also invented the wire rope, for example. You see that at this time, engineers were not focused as we are focusing today in one specific application, but there are more engineers in a broader sense. So later on, we've seen that, I will go quite fast here, we've seen that this continuous loading that we have already discussed is not close to reality. In real applications, we have loads that are of variable amplitude, and we managed, if you like, to do tests, realistic tests after the 1950s, where we had the first closed loop and electrohydraulic testing systems that could really follow a variable amplitude loading. And it was at this period, more or less, between 1925 and 1945, where we had Palmgren and Miner introducing this cumulative fatigue damage rule that we still use today, although we know that for composites it's not very successful in predicting the lifetime. What I was saying until now, it was based on phenomenological investigation. So we're doing a test, we measure the number of cycles to failure, and this is observation, it's phenomenological. In parallel to this, we had also these fracture mechanics investigations. You all know about this. We had Griffiths initially, and then Irwin, that introduced these K intensity factors and the fracture mechanics. So one is the early father, the other one is the father of fracture mechanics. I don't know who is the grandfather or whatever they call, but these persons are those that introduced or put the basis for fracture mechanics theories that we are still using today. And when we talk about fatigue, we talk about Skyde, if I call it well, it's a Dutch professor, and Paris, where they both work for what we call today the crack growth, fatigue crack growth curve. So a curve that shows the relationship between the speed of the crack in fracture and the load that we apply. So the load can be given by using K or by using G. We use G in composite stress strain energy release rate for composites. But there is anyway a component that shows the load that we apply, and on the other axis we have the speed of crack, this dA over dN. So this is a typical Paris law equation. So until now, we didn't say anything about composites, and all these investigations were linked to fatigue of metals. So, and as we said, this comes back to 200 years, initiated 200 years ago. when we talk about composites fatigue, we have to search back to the 1950s, and this comes with the introduction of composites actually in the engineering field. We've seen papers in the 1948, mechanical properties of 5 laminated plastics from Finlay and William. We have another one in 1942. These are the first papers discussing properties of plastics, as I used to call composites at that time. And most of them, if you see, they do comparative studies. In this paper, we say 5 laminated plastics. Here, again, if you go deeper in this paper, you see that they tested, I think, 6 different types of resins with the same fibers to investigate their performance and try to find out which one is better than the other. So it's mainly a comparison. The same was done by Holbert in 1955, where he realized that we have almost nothing published about creep and fatigue, and why creep is introduced, and since so early it has been introduced, because if you remember before, we discussed about this mean stress effect. So you can imagine that in composite materials that are more or less, they have at least viscoelastic behavior at certain ranges of temperatures, or depending on the resins that are used. So we have materials that are viscoelastic. So this means that when we have non-zero mean stresses, we have also a component of creep in the fatigue behavior. And this has been investigated, or at least has been identified as a factor that affecting the fatigue life of composites now, and not metals, already since 1955. So for them, the problem was that we have only a few data and there is inconsistency in data. And then going 20 years later, and probably 50 years, 45 years before today, having Brian Harris in his paper in 1977, saying that there is no general agreement about what kind of data we need to design structures with fatigue considerations. And coming to today, we still have this question. We don't know what kind of data we need. We don't have commonly accepted, if you like, theories for designing composite structures for fatigue. And there is no commonly accepted protocol or standard for data collection and curation. We'll discuss about this later as well. So continuing this review of materials, we've seen that in the past, the composite materials were considering as fatigue insensitive. And fatigue insensitive has been, this characteristic or characterization of composite has been given when people started testing carbon fibers. So carbon fibers at the 0 direction, they show 0 or very minimum stiffness drop during loading, and they saw no damage until close to failure. This is what has been also introduced once in the 1980s as the sudden death phenomenon. It was the phenomenon where while testing unidirectional composites along the fibers, nothing was identified, no damage was identified, and then the material was failing suddenly at a certain point of cycles, or at a certain point of stiffness degradation, without any let's say, announcement before. That's why this was the sudden death phenomenon, and that's why they called the composite materials being fatigue insensitive. We'll see that this does not hold true anymore. So probably you all see, you all know this famous figure about the Boeing 787 that has more than 50% of composites in the body. There's the same happens for Airbus, and we all know that composites are used in aerospace for a lot of reasons. Probably we don't know, we don't have in mind this history of composites and the way that they've been used already from a long time ago, since the 1940s, 50s. in a lot of different applications. This is one chronology of composite usage in aerospace and in different components. We also have this first sailing boat made by Composites in the 1940s, from 1942 I have here, 1942, that really changed the history of boating world because of composites, and this is probably the best proof that composites can be durable and without any problem surviving in seawater or all these aggressive environments that a sailing boat can see. So composites are used in aerospace, are used in a lot of different other applications. The common characteristic of all these applications is that they are all facing intensive fatigue loads during their lifetime. And this is one of the reasons that makes composites and fatigue for composites being very, very significant. Another reason for making fatigue for composites significant is the lightweight characteristic of composites. If I will just bring a very simple example that might be self-evident for everyone. Imagine a concrete bridge that is so heavy that the traffic load is minimal, is not affecting the behavior of the bridge. If we talk about a similar composite bridge that might be 4 or 5 times less heavy than a concrete bridge, then the life loads become significant. And the life loads are always fatigue loads for this application. So we know that fatigue is affecting a lot the behavior of composite materials in different applications. And we know that we have now a lot of structures like wind turbine blades that are supposed to live for 25 years more or less, and they face more than 100 million cycles during their lifetime. We have helicopter blades that are approaching 100 million cycles. We have bridges, ships, depending on the design and the dimensions, they might be more than 10 million cycles, and so on. So we see that we have a lot of composite structures that are facing a lot of fatigue loads during their lifetime. And these structures are massive, are huge. You know about the longest blade. Today, I think it's 120 meters. This was the longest blade a couple of years ago, 107 meters, made by LM for the offshore 12 megawatt machine that they were preparing at that time. So what do we know about composite fatigue? We know that it is more troublesome than fatigue for metals. When we test, we have heating of the material. So we need to test at low frequencies, which means that we need to spend more time for testing for testing composites. We have problems when we test multi-directional laminates or angle ply laminates. We have reorientation of the fibers due to the loading, and this changes actually the material. So it means that we are testing a material that during loading it is changing. So we have to consider this as well. We have important effect of strain rate on material, the material behavior, and it is more significant when we have viscoelastic components. So when we have thermoplastic composites, or we have epoxy composites that are quite matrix which is quite ductile. We have problems with voids in adhesives, misalignment of fibers during manufacturing, or manufacturing defects that can affect a lot the performance of the material. We have material preconditioning problems because the material is very sensitive to temperature, solvents, humidity. So this means that the material and the testing environment should be controlled to avoid having all these effects. We have problems with specimen geometry and a lot of tab failures in composite specimens or adhesive specimens. And we have standards that fail to actually consider these effects. We follow the same standard. We use standard specimen geometries, and we get different results in some cases. So I'll come back to each one of these considerations of composites. And I will continue discussing this knowledge that we have with composites, what we know. And if you see again, we'll go back and we see that although today we are still investigating these effects, we almost know everything since the 1970s. There are publications at that time, this one from Salkin, for example, 73, discussing about the damage modes or the damage progression in composites, comparing to the damage progression in metals, which you see again, it's much simpler. You have one crack that propagates, and at the end, when we reach a critical damage, we have fracture. While for composites, we have a lot of different failure modes that actually they do not appear individually, but they are interacting, and this makes the behavior of a composite material much more complicated than the behavior of metallic components. So this investigation about failure mode started also early. In 90s, we had the first use of optical microscope to investigate fracture mechanics characteristics. 1950s, we had the scanning electron microscope, and today, of course, we use DIC, X-ray tomography, thermographic cameras to investigate all these effects in metals and, of course, in composites. And we can go much deeper. For example, with scanning electron microscope, what we see in this left figure is failure of fibers. When we go macroscopically with DIC, we can investigate and exactly locate the failure before it happens by checking online, I mean, during in situ, if you like, during the test, investigating and measuring the strain at different locations of the specimen. Or we can work with tomography to investigate materials and their damage modes during the in situ in some cases, but also ex situ after failure to accurately investigate the damage location and the damage mode. So continuing to what we know about composites, we know today that they are not fatigue sensitive. Composites do fail in fatigue, and usually they do not show any fatigue threshold. You probably know about metals fatigue. It can be characterized by a kind of SN curve or Wheeler curve, like this red line that I showed here. But if I go back and discuss about composites fatigue, first of all, we have a lot of scatter. And this scatter is related to the effect that I discussed before, the effects that might have, the manufacturing defects that we might have, different material properties due to the manufacturing, due to the preconditioning of the materials, and so on. Actually, in composites, it is widely, let's say, accepted as a rule that we accept as a valid test something that has in the same stress level more or less 1 decade of life difference. So here, if we go from 10 to the power of 4 to 10 to the power of 5, we see that the scattering between this stress level is this 1 decade of life. The same if we go lower or if we go higher. So this is more or less what is conceived as an acceptable scattering composites. In this curve also we can see, or I think I have another one. We see 3 different regions of fatigue life: region 1, 2, and 3. That each one is related to different failure modes, and that's why we see experimentally also that the descent curve is having the 3 different slopes. One big slope in the beginning, a more or less straight line in the middle, and then again slope that is leveling at the end. And this is more or less what we observe for any composite material when tested under fatigue. We also know, and this is very typical schematic diagram showing the stiffness degradation of composites. We know that the stiffness drops initially during this stage 1 of the fatigue life, and it is more or less stable for a long period. This might be probably 80% of the fatigue life, and then drops at the end. The level of drop, so here I'm going close to 0, but in some materials, especially when we have unidirectional materials tested on axis along the fibers, the drop might be 2%, 1%. And when we have off-axis materials, then the stiffness drop is much higher. We also have some other assumptions. We know about composites that they follow what is called the stress life equal rank approach, which is schematically shown in this diagram here. And the idea behind this is saying that the materials are failing in fatigue the same way that they fail in static loading. So if you plot a distribution, so we can see it also here. If you plot if I'm not wrong, here is a Weibull distribution, and in this distribution, the same distribution, we can put all our composite failures, either if they are at static loading, this LC, so the black dots, or they are tested in fatigue at different loading levels. So the idea behind this SLERA, the stress life equal rank approach, is that the specimen that is stronger in fatigue, it should be the one that is stronger in quasi-static loading as well. Although this cannot be validated, because if you test a specimen in quasi-static loading and you break it, you cannot break it also in fatigue. It is something that we've seen with statistical analysis of failures of materials at different loading types. We know also, you remember we discussed about frequencies, and we know that there is a significant effect. Now, when we do tests on composites, we try to keep the frequency low, lower than 10 Hertz for sure, sometimes as low as 1 Hertz, to avoid self-heating. Because if we have self-heating in the material, we see that this is a testing that we did a couple of years ago here at CC Lab. So the self-heating of the material is, so what you see here, the colored plots are are thermal camera plots. The black and white is a normal camera showing the damage of the material. And we see the evolution of damage from 0% to 100% of life, so until failure. And we see that damage initiates at specific points. We see that the material becomes darker here, so the translucency of the material is not the same anymore. And at the location where we have damage, we have also increase of temperature. And this is because of the internal friction that comes when you have damage, you have cracks, and the material starts creating temperature, heat, because of the friction internally in the structure. So what we know today is that there is an effect of this frequency of the material behavior. When we exceed a critical, if you like to call it like that, frequency, we have temperature increases and the life decreases because we soften the material actually. When we go to low frequencies, and if we go to very low frequencies, then we have creep fatigue interaction, because if we test at very low frequency, it means that we keep the material at a certain load for a certain time, which means that we introduce, in addition to the fatigue loading, we introduce also creep effects. So actually the optimum is to find for each material, and this is not self-evident, but we have to do preliminary testing to find out which frequency is the most appropriate for testing its specific material under investigation. We know also about these viscoelastic effects that we discussed before. We know exactly what I said before, the effect of creep, or the effect of the opposite of creep, so relaxation of the material. As we said, composites are viscoelastic, and as we proved a couple of years ago again with another investigation that we did, we saw that if we stop the testing So imagine that this is a continuous testing up to failure. And this continuous testing is producing these red dots here in the red line. So what we did the same amplitude, but we were interrupting the test every 20% of the life, of the average life at its stress level. What we've seen is that the life of the material has been extended by a factor of more or less 2, which means that there is a significant effect of this relaxation. The material relaxes when we stop the testing and recovers. And then we can start again at the same loading level, and we can extend the lifetime. We did the same also doing the opposite, keeping the loading at a high stress. So introducing creep, and we introduced creep for 2 hours and 48 hours. And the effects are shown also here in this graph. The continuous loading is the black curve in the middle. And what we've seen here, which is quite interesting, is when we stop the test only at 2 hours and introduced very short creep component, we've seen an increase of the lifetime, which means that this short stop actually helped the material recover instead of making the behavior worse. But when we introduce long creep components, so creep loads for longer times, we've seen that the behavior has been worse. So the lifetime has been decreased because exactly because the creep was dominant in these loading cases. What we are trying to do now is to investigate also the performance of the material, to see this effect of the viscoelastic performance of the material on the fatigue life. And this is work in progress. I will not go into details, but we've seen significant effects of this viscoelastic behavior. And here we are analyzing the behavior of the material if we consider the true or the nominal strains that are we are measuring on the material during the testing by DIC. So we know also that Goodman, that we discussed before, is not anymore the Goodman. He's not good anymore, because the Goodman diagram that was suggesting a straight line between the known SN curves, actually, the SN curve for R minus 1, R equal to 1, does not exist anymore, does not apply for composites. We've shown years ago that for composites, we need to discuss about these constant life diagrams. So diagrams of this type. For those that are not familiar with this, I will describe a bit. We'll say that here we have the main parameters of the diagram. So the mean, you remember we discussed about the mean stress of a loading, the amplitude of the loading, and then we have this R ratio that is actually the ratio between the minimum and the maximum stress. Imagine that we do this testing. So the minimum stress is this value and the maximum stress is this value. The ratio between these two gives this R ratio. So we have R ratio minus 1 means we have reversed loading. We have R ratio equals to 2 means to 0, or we go from 0 to a maximum of positive stress. R ratio minus infinite, we go from minimum something at the minus, so negative, to 0, which gives this infinite here. And we have 3 sectors in this diagram. The right sector that shows only tensile testing, the left sector that is compressive, and then intermediate here we have tension compression or compression tension on the other side. So we know now that if we use this kind of diagrams, we can use them as predictive tools, because theoretically we can predict an R ratio, so an SN curve actually, or an R ratio that is not known during the testing. So for composites, as I said, Goodman diagram is not anymore a good one, a good selection. That's why here we use different types of diagrams. We published again this, depending on the material. There is different diagrams that are the best. But what I wanted to point out here is that these diagrams show also the difference of the material behavior in tension and compression. So depending on the material, it might be that the material is more susceptible to failure in tension or in compression. And what we can collect this information by drawing these diagrams. We also have this behavior, this information where you remember before we talked about fatigue and creep interaction. So when we reach R ratios that are close to 1, we have more creep components. When we are at R ratio -1, theoretically, we have only fatigue because there the mean stress is 0, actually. So what we also know about composites is that we have to use multi-axial stress states. Even in uniaxial loading, when we have an off-axis material, we can simply calculate the multi-axial stress field in the material itself, which means that even for uniaxial loading, we have multi-axial stress states. And actually, it was around 20 years ago that we introduced this concept, and we actually somehow imposed the change in the design codes for wind blades, for example. Until more or less 2000, the main stress component that was used for design was the sigma-1, so the normal stress, where we have shown that if you have very minimum, you see, N2, so normal stress in the other direction, and N6 is the shear stress, that are very, very few compared to the sigma-1, the N1 in this case. These components can still give significant effects to the failure of the material. So it was significant. It was necessary to consider all the stress components for designing composites in fatigue. We discussed also before about the specimen type, and we know today that there is an effect of the specimen type. There are standards saying that the specimen should be rectangular. There are investigations doing dog bone specimens, finding, for example, in this paper from the group of Paul Bronsted, they found that there is an effect if you use different types of dog bone specimens. They found better behavior compared to the rectangular specimen in fatigue, and they scaled actually the results by considering the stress concentrations that they had. So the result from this paper is that if you consider the stress concentrations, you can alleviate the stress concentration in the rectangular specimen, then you can probably have a rectangular specimen that gives good results. We also, as I said before, we did some tests following the ASTM standards for adhesives, so polymers, and using 3 different types of specimens, we realized that the result, especially in fatigue, is not the same. Although the standard suggests that you can use either 1, 2, or 4, so type 1, type 2, or type 4 specimen for doing the testing. So we know also that when we use composites and polymers in different applications, now we have, as an example here, this wind turbine rotor blade. And we know that this is completely different than what we've seen until today, and it's different than the structures that we have when we have the metallic materials. So the approach is different. We have new materials used, we have new geometries used, we have new types of joints. So now we talk about thick adhesive joints. Imagine in aerospace, aluminum joints with film adhesives of 1 millimeter thickness. Now we talk about joints that have 10 millimeter of thickness or even 30 millimeter of thickness. We have reports discussing about 30 millimeter of thickness in wind turbines. And of course, we know that these joints are made with very, allow me to say, primitive techniques, have nothing to do with the joints in aerospace that follow specific protocols. And there we have a lot of voids, we have a lot of manufacturing defects in the joints, and the idea is to secure or to guarantee the lifetime of a huge structure like a composite rotor blade, having in the body joints like that. So additional information is needed We don't know. Here is what we know. We know that we have new materials and new geometries, but we don't know yet how these materials and these geometries are performing. We've done some testing. We are working on that. And we've seen that the voids, so this is a micrograph. These are percentages of voids in the materials, different percentage of voids. So a lot of voids, less voids, or few voids. This, although it seems a lot, it's less than 0.5% of voids in the bulk of the material. And we see that the presence of voids can significantly change the crack path in the material. In this case, where we have a lot of voids, the crack path is changing a lot, shifting from the mid-plane. In other cases, the crack can initiate from voids, or the crack can more or less be in the mid-plane when the voids are fewer. So I discussed before also about fracture mechanics. And of course, in composites, we have a lot of fracture mechanics used. There is a big discussion about using the G, the strain energy release rate, instead of the K, the stress intensity factor, especially because for composites, it's very difficult, if not impossible, to calculate successfully K values when we have cracks with large process zones and so on. But anyway, we did tests. We are doing tests, a lot of tests, mode 1, mode 2, mixed mode testing for composite laminates, for composite joints, that as this case that I'm showing. This is again from work that we did here at CC Lab 10 years ago. And we produce FCG curves. We produce R curves for static loading. We produce FCG curves, and also we develop models to fit this behavior. Here again, there is a discussion about what kind of parameters should it be. It can be G, it can be, so I will just go to the next slide. So it can be G, it can be delta G, it can be square root of G, or another parameter that defines actually the load that we introduce, the load that we apply to the material. And on the other side, we have the fast, so the speed of the crack propagation. And you see that in a lot of cases in these graphs, we have a kind of a fatigue threshold. We have a kind of bending in the stress in the curve when we approach values of cycles 10-6, 10-7, means that the crack propagates 1 millimeter every 10 million cycles. In this case, 10-7, which for a normal application, this can be assumed as a fatigue threshold, that the crack does not propagate anymore. So we also used multi-axial failure criteria in this case, and we can investigate the behavior of joints from the same materials as those that we tested in mode 1, mode 2, and mixed mode. And we can estimate for these joints, in this case is the behavior of the G propagation during the loading, or this can be also extended for fatigue loading and investigating the behavior of this joint in fatigue. So creating actually an FCG curve for the joint. So what is expected? And I'm close to summarize. What do we expect actually with these fatigue investigations? It is expected to actually take out this red line. There is a red line between the observation, the models that we have for our structures, the models regarding the material used in structures, and the material data that we collect. And here, if I remove this line, I have the calculation of stresses in the structure. I have theories like this, what we call a CC fatigue is a theory that we are developing internally here in the group that can give us actually a safety factor, if you like, to call these dots here for every section of or every position on the blade. So actually, what is missing is the link between the information that we have at the material level to the fatigue life prediction of new or existing structures. And this fatigue life prediction of existing structures, it might be equally or if not more significant than the fatigue life prediction of new structures, because it is related to the extension of the lifetime of structures, which is if we go a bit deeper, it is related to the sustainability of engineering applications that everyone is discussing these days. So to conclude, I will just go very fast. We know that fatigue is very, very bothersome. It's a big problem in designing of engineering structures. We know that now most of the structures are failing due to fatigue or fatigue-related phenomena, as we said before. Unfortunately, for composites, this investigation is more complicated because we have synergetic effects that are acting all together, and one is affecting the other. We cannot isolate effects as in metals. We have a crack that propagates and leads the material to failure. We know, and there are a lot of different approaches to discuss about fatigue. And we know that, unfortunately, there is a lack of experimental data to validate these approaches. So we've seen a lot of publications. There is a method, there is a theory, and there is a validation by using a short term or a small data set to validate this theory. And then this theory cannot be used for another material or cannot be used if one parameter is changing. So this is probably what is missing from what we are searching. Today we are standing on the theoretical approaches that exist, but we don't have one that is commonly accepted by everyone. We have a lot of challenges, as we said before, about sharing composite fatigue data. We don't have homogenized protocols. We don't have standards for this. We have even standards that are not, as I said before, are not reflecting, if you like, exactly the behavior of the material itself. And of course, we miss databases, and for both data, for experimental data, but also for theoretical models, and we miss the sharing of information. So I know that Sena likes this photo. I just brought it here because I wanted to say that probably whatever we do, as far as we try, we will never be able to make something so beautiful and so durable, like what they did 3,000 years ago, more or less. What we can do, what we can say is that we already identified the challenges about composite fatigue, and now probably we know, at least some of us, we know that we have to work together for this, for addressing these challenges and progressing in this field. I think that we are in the middle of somewhere here. We are not starting now. We are following what others started, and we also did the last couple of years, and we're progressing in a good way. I hope I didn't make you so much fatigued that you are collapsing like this. This friend of mine here. I'd like to thank you for your attention. And if you have any questions or comments, you're welcome to join now or send me an email at any time to discuss.